Hello, everyone. My name is TJ Willits from Veolia Water Technologies. I'll be the moderator for today's webinar, which is called Biology and Chemistry 101 for Anaerobic Digestion Systems. Just want to let you know that this is the first webinar of what we hope to be several webinars in our Anaerobic Operator webinar series. This exclusive webinar series is invite only for our customers or people that we've done business with. So we're really excited to really build upon today's webinar within this community here, which you make up. There are several dozen of you on the line here. So we did mute your lines, but no worries. We have thought through that. And if you look, you should see on the right-hand side of the panel there's a question box. Feel free to go ahead and put your questions in there. Some people have asked if they would receive copies of the webinar. The webinar is being recorded and it will be distributed tomorrow within a follow-up email that we send to all the participants who've registered or the people that have registered and not attended. So you'll receive a copy of the video of this webinar. Just one other tip, if you are having issues connecting to the audio, you can either connect using your speakers, or if you click the phone call button, you'll be able to have a conference call and ID. So you'll be able to log in that way. So you should be hearing me now. If you aren't hearing me, please go ahead and try to connect to the phone call if you're having issues with your computer audio. Before we get started, we just want to let you know that we are hoping that you are not just an attendee of today's webinar, but you are an active participant. What we do have set up is after the webinar and also in the follow-up emails, there's a link for a survey that you could take for the webinar. And what's great about that is you could help put your input and feedback and suggest and recommend topics that we'll consider for future webinars in the next coming months. We're hoping to do these either quarterly or bi-monthly, depending on the participation. And we'll also let you know after the webinar when the next webinar is scheduled. Also, we are going to allow and provide participation certificates if you want to collect those for your continuing education credits. In the survey, please, there's a question in there that asks if you want us to create a certificate for you. And if you go ahead and check yes on that question in the survey, we'll email you a PDF of the certificate that you could file for your records. One last piece of housekeeping before we get started with today's webinar. We just want to let you know that if you like what you hear today, we're doing a very deep dive webinar called Water and Resource Conservation. It's mainly geared for food and beverage and related professionals out there. So it's going to be similar to what the type of content that's here today, but it's going to be covering several different technologies and also talk about different water reuse strategies and other ways that you can look to optimize the resources within your various facilities. It's scheduled for May 22nd, and that's going to be in Portland, Oregon. If you are interested, we're getting ready to send out the invites, but if you want to shoot me an email, there's my contact information on this slide, and I'll make sure that that we'll go ahead and get you on the list to attend that. So before we begin, I wanted to start and introduce you to today's speaker. The first speaker that you hear today is Miss Jill Jordan. I'm sure many of you are already familiar with her and maybe have met her or worked with her in the past, but Jill has over 35 years experience in anaerobic treatment of industrial wastewaters in all types of systems of the anaerobic type. And in fact, a fun fact for Miss Jordan is that she was on the startup team for the very first UASB system installed in the United States, and that was in 1981. In addition, she's started up over 60 facilities in her career, and she is definitely excited to share some of her knowledge with you today. Joining Jill is Mr. Rob Franken. Rob Franken has over 30 years experience as well within the development and commercialization of water treatment technologies. And Mr. Franken's current role at Veolia is to lead the commercialization efforts for our extensive biological and wastewater treatment technology portfolio, including the biothane technologies, as well as some of our other biological technologies, such as our MBBR. So with that, I'm going to hand this presentation over to our first speaker, Miss Jill Jordan. Jill, are you with us?
Yes, thanks, TJ. Hi, everybody. first of all, let's go over what the agenda is going to be today, what we're going to cover. We're going to talk a little bit about what we're treating and why, how do we measure what we're treating, understanding the two types of bacteria in an anaerobic system, and how to keep the bacteria happy. Next. Next, TJ. Thank you. So, why do we even care about wastewater treatment at all? Most of you are from the food and beverage industry, so we're eating your product, so why isn't it okay to just dump it out into a river or lake that's nearby? Who cares? It's edible material. Well, if we did that, those substances, which are probably mostly carbohydrates, proteins, fats, sugars, things like that, would go into these rivers and streams, and the bacteria that are in there would want to eat that. I mean, we want to eat it, so the bacteria would want to eat it also. But those bacteria, in eating that material, would uptake dissolved oxygen that's in those lakes and streams. And if all the oxygen was removed from those rivers and streams and lakes, the fish would die. So that's not a good thing. Also, I don't want to be swimming in beer and French fries and potato chips and vegetables either. So that's why we want to treat these wastes in a responsible manner. Next. So let's determine how much of this pollution, let's call it, that you're going to be sending out. How do we measure that? Well, we just said that the bacteria in these receiving waters take up oxygen. So the easiest way to determine how much pollution there is how much oxygen demand there is, because the more pollution that there is, the more oxygen would be taken up in these receiving waters by these naturally forming bacteria. So we're going to measure the oxygen demand to determine the amount of pollution. Next. So there's two classic ways to measure the oxygen demand in a wastewater. The first is the BOD5, which is biological oxygen demand. The 5 means it's a 5-day test, not necessarily a good thing. But let's describe how this test is done so you know how it works. You'll see the BOD bottles on the right-hand side of the screen. You take water and you put a little fish stone in there and you aerate it until it's saturated with oxygen at room temperature. And you put it into these bottles with a little bit of bacteria, some nutrients, and your sample of wastewater. You measure the dissolved oxygen, you put a lid on it, and then you put it in an incubator at 20 degrees C for 5 days. After 5 days is up, you come back and you measure the dissolved oxygen that's left in that BOD bottle, and the difference between the start and the end oxygen level is the BOD. Pretty simple, except there's a lot of things that can cause it to go wrong, and it's a 5-day test. So in most cases, in anaerobic wastewater systems, the water's only in the system less than a day. So waiting 5 days to get an answer on how much you fed a system is not necessarily a good thing. So the second way we look at the oxygen demand is the chemical oxygen demand. And I think most of you are familiar with like the Hawk COD measurement files, which are shown on the bottom of the right-hand side of the slide. And here you take a small amount of your wastewater, put it into this vial that has some sulfuric acid, potassium dichromate, and some mercuric sulfate in it. And you mix it up, shake it up, cook it for 2 hours, and the orange turns to green, which is the chromate going to chromium, and the amount of green determines the COD. Now, the COD test doesn't just measure what can be eaten biologically by bacteria. It also measures any other chemical compounds that could be reduced in this acid environment. So the COD number is always, for all intents and purposes, larger than the BOD number. But for any given wastewater, there is a relationship between the BOD and the COD. And in most food production facilities, that ratio of COD to BOD is usually something about 1.6. Now, recently, there's been a new way to measure the amount of pollution in a wastewater stream, and that's called total organic carbon. And you notice the BOD and COD are measured in milligrams per liter of oxygen, but the TOC is measured in milligrams of carbon per liter. Because all those substances that we were talking about, like sugars and proteins and carbohydrates, all are carbon-based molecules. So this equipment measures the amount of carbon in the wastewater. And again, that can be related to the oxygen demand. There's a relationship between the TOC and COD. And this TOC is usually a number a lot less than the COD, but for any given wastewater, there is a relationship that can be obtained. Now, the good thing about this is that not only are there lab meters that measure the total organic carbon, but they are inline meters also, and they can be used to help you control your anaerobic system. So I wanted to bring that to your attention. Next. So there's two types of biological wastewater treatment. There's aerobic and anaerobic. Now, aerobic is the type of wastewater treatment that all municipalities use in the United States. And here, bacteria in the presence of oxygen convert the soluble, biodegradable compounds into biomass, which is sludge, water, and carbon dioxide. And anaerobic, which is the emphasis of our webinar today, the bacteria in the absence of oxygen convert those soluble, biodegradable compounds into biogas, which is methane and carbon dioxide, and a little bit of sludge. So let's compare the two. Next. So aerobic. Let's take 100 kilograms of COD, or think of it as 100 kilograms of sugar. And if we treated that 100 kilograms of sugar aerobically, we would have to add about 100 kilowatts of energy in the form of air blowers to keep air into the system. And we would generate about 30 to 60 kilograms of sludge. We would generate carbon dioxide that would go off into the atmosphere as a greenhouse gas. And we would have some really nice clean water. There would only be about 2 to 10 kilograms of COD left. So the deal here is that I have to add energy and they make a lot of sludge. So it's sort of like I'm changing one form of pollution into another because now I got to get rid of the sludge. But the water is clean enough to go into a receiving water. Now on an anaerobic system, I'm going to take that same 100 kilograms of sugar, or COD if you will, and treating it anaerobically, I would about 80% of it would go to the production of biogas, which is methane and carbon dioxide. And methane, if you don't know, is natural gas. So you can actually use the biogas generated in the anaerobic system in a boiler. You can use it in a dryer. You could use it in a generator. You could use it in a combined heat and power system. There's multiple uses for this energy that's produced by the reduction of the compounds in your wastewater. And also, I'm only growing a little bit of sludge. So now I only have 5 kilograms of sludge to get rid of compared to the 30 to 60 if I treated the water aerobically. And unfortunately, in the anaerobic system, I have 15 kilograms of COD left. So it's not quite clean enough to go to a receiving water, but it's usually, I'll say, 80 to 90, 95% cleaner, which is very, very good. And I get the energy. So I have a low sludge production and I have energy credits. Okay, so let's talk about the anaerobic bacteria. There's two basic types of bacteria in an anaerobic digester. There's acid-forming bacteria and methane-forming bacteria. And you need both to make the system work. They work together to degrade the soluble compounds in the wastewater. Next. If you look at the flow diagram on the right, this describes how all the basic processes that let's say a molecule of sugar or protein has to go through to be converted into methane and reduce the COD. We're going to talk about each step as we go on now. Next. The first steps of this digestion process are done by the acid formers, and they really do three things. They do hydrolysis, acidification, and acetogenesis. And what you want to remember now is that the acids reduce pH. Next. So the first step in the acid part is hydrolysis. Think of this as taking a big molecule that's not dissolved in the water and breaking it small enough so that it dissolves in the water and makes it easier to digest. So this is like taking a starch molecule and making it smaller so that it's dissolved in the water. Next. The next step is to take these soluble, smaller molecules and converting them into fatty acids. This is called acidification. And the fatty acids that it converts these materials into are acetic acid, propionic acid, and butyric acid. The third step in the acid formers is acetogenesis. And now we're going to break down the propionic and butyric acids into acetate acetic acid and some hydrogen and carbon dioxide. The final step in the process is methanogenesis. All the acid formers did was convert big molecules into ever smaller molecules. We haven't reduced any of the COD up until this point. So now the methane former's job is to convert the acetate and the carbon dioxide and hydrogen into methane. It's not until you make the methane that you reduce the COD. Now, if you look at the picture on the flow diagram on the right, you'll see that there's two acetates that go to methane and only one hydrogen and CO2 that goes to methane. So most of the process goes through the acetate step. And you can see the chemical formulas up on the left-hand side. The top equation is the CO2 and the hydrogen. They form methane and water. And the acetic acid molecule, the next equation down, goes to methane and carbon dioxide. Again, it's only when you make methane that the COD is reduced. So let's compare the two living conditions, if you will, for the two types of bacteria. The acid formers, again, do hydrolysis, acidification, and acetogenesis, and they live in a pH range of 3 to 8. And they also live in a temperature of 2 to 40 degrees C or 36 to 104 or so degrees Fahrenheit. And they reproduce every few minutes to every few hours. So they can work really, really fast and make a lot of acids quite rapidly. Now the methane formers, on the other hand, just do that one step, methanogenesis, which converts the acids or the CO2 and hydrogen into methane. They are much fussier. They really work best in a pH range of 6.8 to 7.4. They live in a temperature range that's narrow, about 32 to 38 C or 90 to 100 degrees Fahrenheit, and they only reproduce every few days. It turns out that these methane formers are actually the rate-limiting step in this whole anaerobic digestion process. To show you how the temperature affects these bacteria, this chart shows you the relationship between activity and temperature. So you can see the highest activity is around 35, 95 Fahrenheit, and as the temperature drops, say, to 25 C, which is about 75 Fahrenheit, the activity of the biomass is about half, which means I would need twice as much sludge to treat the same amount of wastewater as I would at 95. Notice that the slope of the line on the high temperature side is much steeper, meaning that the bacteria lose activity much faster as the temperature increases above 95. Next. We have a similar curve showing the relationship between the activity of the biomass and pH. The best pH is about 7.2. That's where the bacteria is most active. As the pH drops to 6 or goes up to about 9, the activity goes down almost exponentially. So it's really important to keep the pH in a nice range. Next. Now, we talked about that there were two types of bacteria in an anaerobic system. Well, turns out I was lying. There's a lot more, and one of the next bigger ones that we have to concern ourselves with is sulfate-reducing bacteria. And they are always in the system. You can't do anything about it. as much as we would like to, and their job is to convert sulfate into sulfides. And the problem is that sulfides can be inhibitory to the anaerobic bacteria. Think about before there was penicillin, people used sulfur drugs because they killed bacteria. Also, they remove COD that's not turned into biogas, which isn't a very good thing. So for every milligram of sulfate that's reduced, about 0.67 milligrams of COD is reduced that goes to converting that sulfate to sulfide, but doesn't go to biogas. And if you're trying to use your biogas, that's not a good thing. The other thing is hydrogen sulfide smells. It's that yucky, rotten egg smell, which nobody likes. And also the sulfides can cause corrosion problems downstream in a sewer system. So it's something we have to be aware of. Next. So the question is, how can we make this anaerobic system work when there's two different types of bacteria requiring very different living conditions? And the answer is you have to make the living conditions favorable for the more sensitive methane formers for both to work well. Sometimes we even have to let the acidification step start a little up front so that we can get some of these larger proteins and larger molecules like proteins and fats or anything like that to break down before they get into the digester. So I'm going to turn over the webinar over to Rob now, and he's going to talk about system stability and how to make bacteria happy. Rob?
Yeah, thank you, Jill. So Jill talked about the several types of bacteria that we have in systems to digest COD to biogas. How to do that in a very stable manner is the key to a successful treatment facility. I think it's clear from Jill's presentation that volatile fatty acids is one of the intermediates in the anaerobic chain, and really you don't want to see those anywhere because they have to be converted to the methane. So what you can see is if you look at anaerobic digestion or anaerobic treatment plants, that we always look carefully at the VFA, volatile fatty acids, level in the effluent because it is an indicator of health of the system. And that is obviously because the rate limiting step is with the methane production. So if they cannot cope with the product of the acid formers, then the system is not in balance, it's not in the right equilibrium. So let's look a little bit more in detail on what makes these bacteria happy, because if we want to use those bacteria for our treatment process, we need to make them as happy as we can. And we'll zoom in on these four factors that are on this slide: food, nutrients, climate conditions, and toxics and inhibitors. Let's look at the food first. So COD really represents carbon. So the carbon in an effluent that represents a pollution, we convert it into methane. And the bacteria will not take any carbon. It has to be from some organic source. On this slide, you get a sense of what types of carbon these bacteria can eat. It is, of course, all of the different COD sources from food and beverage industries can be treated. Also, the COD in sewer can actually be treated with anaerobic process, but that is at much lower concentrations. And also, of course, sludges, like for instance, activated sludge can be digested into methane. But for the purpose of this webinar, we're going to zoom in a little bit more on the industrial wastewater side of that business. So, as I said, COD represents carbon, and bacteria will not grow on carbon alone. It's just like any other living being. It needs more than that. In particular, nutrients. There's two types of nutrients, macro and micronutrients. The macronutrients on the next slide, we need that in a pretty substantial amount because cell growth only is done by bacteria if there is the proper amount of nitrogen. So if you look at the nitrogen content of biomass, and maybe at this point I should explain that sometimes we call these bacteria biomass, sometimes we call it sludge, sometimes we call it bacteria. So I'm using those terms through one another. And in this case, I say biomass, 8 to 10% of that material is nitrogen. And if it is not present in wastewater, we have to add it. Same for phosphorus, for instance. Lower concentrations are necessary, but it is an essential nutrient that is required for optimal performance of these bacteria, and that's what we want. We want them to be happy. Micronutrients, like also, again, as any other living being, they need micronutrients. There are quite a few constituents that you can see here on the periodic table that are required. Some of them are in somewhat substantial concentrations, like sulfur, sodium, potassium, calcium, magnesium, and iron. Others are in much lower concentrations, like the typical metals and that you see there. For some wastewaters, all of these nutrients are already available when it comes to the treatment plant. For other wastewaters, they are really deficient. Like you can imagine, for instance, condensate wastewaters. They don't have any of those nutrients. And in that case, we really have to add it to the system to make those bacteria happy and let them perform in a most efficient way. Jill explained that some of them are sensitive, maybe more sensitive than the others, but they're all sensitive to climate conditions such as temperature and pH. So when we operate or when we design and engineer projects that should do this treatment, we need to take good care of the climate conditions and to make these bacteria happy. So for some wastewaters, we have to add caustic, for instance, or magnesium hydroxide to increase the pH. In some rare cases, doesn't often happen, but sometimes we also have to reduce the pH, and then we can use, for instance, hydrochloric acid. And for the reasons that Jill explained, we'd rather not use sulfuric acid for that purpose, because that will give us the issues on the sulfur side. Temperature control is important, so we typically run in mesophilic conditions. There are also plenty of digesters that run at thermophilic conditions at higher temperatures. In any event, these temperatures should be controlled, and the heat exchangers, for instance, can be introduced into a project to make sure that there's not a high operating cost associated with heating of influent or heating of sludge. The last factor that I want to zoom in on to make sure that all our bugs there are happy is that we cannot have any toxic components or inhibitors in wastewater. Now, many of you are from food and beverage type industries. You use CIP regimes in your factories to clean out equipment, and you use chemicals for that. Not all chemicals are good for the wastewater treatment plant or for the bacteria that are involved in our process. So, give you an example, quaternary ammonia compounds are often used in factories that have a negative effect on the performance of anaerobic bacteria. So they should be really be monitored and eliminated if necessary for the good treatment. So that is also something that is important, and we can do all sorts of testing, for instance, when we have issues in plants to sort out what is it that causes toxic effects or inhibition. So remember, all of these bacteria that we have in these systems and that perform these reactions for us and clean up the wastewater, none of them are genetically modified. The whole philosophy of this type of treatment is that you select by natural selection, you select for these bacteria that grow well and are happy in the systems. So by applying those conditions of temperature, pH, the type of nutrients, the type of food that you give, the right bacteria will develop in the system, and you will just select for them, and any bacteria that is not there to do any good, that will eventually leave the system with the effluent. So I'm coming to the conclusion. So if we, a little bit of a wrap up. So Jill explained that we have several types of bacteria in our systems that perform these reactions to get carbon into methane form and reduce COD of wastewater. The main species of bacteria can be categorized into two categories: acid-forming bacteria and methane-forming bacteria. The methane formers are slower and in a way a little bit more sensitive. So we have to make sure that they are very happy so that they can cope with the products that are formed by these acid formers, and so that they can produce the methane that comes out of the water. And for them to be happy in that, they need to have all that conditions well controlled in terms of pH, temperature, nutrient compositions, and certainly no inhibitors in the system. And in all of these systems, when we create those conditions, then we have a happy lot of bacteria, and they will perform these reactions, and we will remove and eliminate the COD from the wastewater. So I think that is where I want to conclude this part of the webinar.
Great. Rob, Jill, thank you so much for sharing all that knowledge with everyone here on the line today. We have allotted some time for questions. There's a box probably on the right-hand side of your screen that you could go ahead and type in questions, and we're going to try to get to as many as possible here in the next couple minutes. I'll allow you to give you some time to go ahead and type those questions in. In the meantime, I just wanted to make you aware that our next webinar is scheduled for Thursday, May 24th, and the topic for this webinar is going to be entitled Operational Efficiency of Anaerobic Reactors for Wastewater Treatment. So it's going to be a great webinar, should help you put some tactical things in place for your own plants if you have an anaerobic plant that you're operating. So also just want to put another reminder out there to please take the survey after the webinar. It'll help us make these as valuable as possible for you. And also that's where you'll request a certificate if you would like a certificate. Okay, we're ready to start taking some questions, and I got an initial question, and that initial question is that you mentioned the effect of sulfur in wastewater, and what is the maximum sulfur concentration that is tolerated by the bacteria?
Thanks, TJ. That's a good question, and it's actually related to the amount of COD in the wastewater. The sulfur gets into be equilibrium between the gas phase and the liquid phase in the system. So in the water phase, you don't want the H2S concentration to be above like 250 milligrams per liter. And that works out to be a amount of H2S in the biogas of about, let's say 2% or so. If you want to look at it on a ratio basis, the COD to SO4 ratio should be greater than 4 to make sure that your the amount of sulfur that would be generated would not be toxic to the system. I hope that answers the question.
Thank you, Jill. Another question that we have is related to sulfate reducers, and this participant wanted to know sort of the figures about related to sulfate reducers in terms of 1 to 0.67. So can you confirm that amount?
Yeah, for every milligram of SO4 that's reduced, 0.67 milligrams of COD are used to do that reduction.
Okay. Another question also is related to peracetic acid, and if there's peracetic acid at 40 ppm inside the reactor, what is the effect that would have on the bacteria and the risk of killing the biomass?
Yeah, Rob and I are looking at each other. Peracetic acid is also known as PAA. It's very bad for the anaerobic reactor. 40 milligrams per liter would certainly be inhibitory, if not toxic, to the anaerobic biomass. And again, it's related to the amount of COD. I'm sorry, I don't have the right relationship right in my head, but I can get you that in an email. But it's very bad. It's not quite as bad as quaternary ammonia compounds, though.
Okay, and we'll follow up with that person that asked that question. A question related to if would higher solids and or more complex polymers in the wastewater, increasing hydrolysis, increase the sludge generated?
It really depends a little bit on what type of solids it is. I mean, some solids, give you an example, insoluble starch, we know that is completely solubilized and acidified and also completely converted into methane eventually. So that is a type of solid that will not produce a lot of sludge. But if you have other solids, especially inert solids, you know, some wastewaters also contain inert solids, they will end up in the sludge eventually. So it really depends on the type of sludge that goes into the system. It also depends on the residence time that you have in your system. Of course, if you go to conventional sludge digesters, they operate with residence times of 20 to 30 days. Then, of course, you get a much deeper conversion compared to high rate anaerobic systems where the residence time is literally can be a matter of hours. So there's no simple answer to that question. We would have to look at the specifics of that situation.
Thank you. Another question is if you could discuss a little bit about the VFA alkalinity relationship and how it varies from 0 VFA and 11.0 alkalinity, then goes to say that 0 and 20 alkalinity, what might be going on in the system and where should they start to look for troubleshooting that issue?
Well, to be honest with you, I never look at the relationship between the fatty acids and the alkalinity. To me, it's much more important to just look at the absolute value of the volatile fatty acids. And as long as the absolute value of the volatile fatty acids is less than 5 milliequivalents per liter or 300 milligrams per liter of acetic acid, I'm a happy camper, and so are the bacteria. Because you can have, with that 0 VFA, I could have an alkalinity of, say, 15 milliequivalents per liter and be fine, or I could have an alkalinity of 50 milliequivalents per liter and still be fine. So I always think it's better to look at the absolute value of the VFA alone. Maybe Rob has. I only can add to that. I mean, if you have a higher alkalinity in your anaerobic effluent, it is also an indicator of a more stable process. If your alkalinity is really low and something turns sour, then it turns sour really fast. So it's better in that sense to have a certain minimum level of alkalinity in your anaerobic effluent.
Okay, thank you. And another question, a very common question, has to do with quaternary ammonia, and what is the max ppm for that substance?
I always say 0. I mean, and I don't mean to be flippant about it, but it's just so bad for the anaerobic bacteria. It's just, I don't even like to have it on site anywhere. But realistically, you can take some, and the more sulfur you have in the water, the more you can take. But it's a very tricky thing to work with, to say that, oh, it's okay to use the quaternary ammonia compounds because they have, Y amounts of sulfur in my water, so that'll take care of it, because you're never really sure. So in my opinion, it's just better not to have it on site at all. It's that bad for the anaerobic bacteria.
Okay. I have a question here related to fog and talking about how it affects the UASB and if it is possible for the UASB to do removal of fog in that system.
UASB is a system that is particularly designed for soluble COD removal. So if you have, in the dairy industry, of course, we have plenty of wastewaters that contain fog. In that case, you either go for a low-rate anaerobic system that tolerates high fog levels and convert it in a more conventional low-rate system, or we would pre-treat it most likely with a kind of a flotation system up front to make sure that we don't get any fog into the UASB. Because if you do get fog in the UASB, then it will tend to stick to the granular sludge, and that will change all the properties, and it will be inclining to float. and that is not good in a UASB system. So our tolerance level for fog for UASB is really low. You should be thinking less than like 75 ppm or 100 max in a peak condition.
I just so if somebody doesn't know what fog is, it's fats, oils, and grease. Because there may be some people that aren't familiar with that term.
And sort of a follow-up question on that fog. Would it pass through? Does it accumulate? You mentioned it sticks to the granulars and will float to the top of the reactor. Is it just best to just put a piece of equipment before the reactor to try to knock out as much fog as possible? Is that your recommendation?
Yes. If you want to treat a wastewater which has fat, oil, and grease, then you need to pre-treat it. The best way we do is use a flotation system, dissolved air flotation system, for instance, so that you keep that fog level below 75 ppm. That's our rule of thumb.
Okay. I have a question, shifting gears to talk a little bit about polymers. What kind of risk do polymers play to the bacteria? Should they be careful about certain types of polymers, or is there specific compounds to look for that are common in polymers that would end up in the wastewater?
Well, that's a really good and difficult question to answer. I mean, you'd have to know where the polymers are coming from, because most of the time I've seen polymers, let's put it that way, is in some sort of solids removal system, in which case the polymers go out with the solids and wouldn't be going into a high rate system. But if you're digesting those solids that have the polymers in them, yes, you have to be very careful that they're not toxic to the anaerobic bacteria. And there's so many different polymers out there, and I mean, we've tested some, and you could say they're all high weight, gram negative, or something like that. And some of them are, and some of them aren't toxic. It's just, I don't know. You have to test them. And the other thing is that I want to say is, a lot of times you need to use a flocculant and a coagulant in your solids removal upstream. And if you're, again, using those solids in a solids digester, you need to test the combination of the two, because individually the flocculant and the coagulant could be not toxic, but together that they are. So it's something that really needs to be tested on an individual basis.
Okay. A few more questions left here. This is regards to with a higher alkalinity, could your VFA number go higher and your system still be operating stable?
Not really. I think what Jill just said is that we have this rule of thumb of 5 milliequivalent.
Yeah, that's why I don't use that ratio, because that ratio can give you false good feelings, because you can have a high VFA that tells you that your methane formers aren't really keeping up with the acid formers like they should be. So. But the ratio of the VFA to alkalinity is okay. That's why I go more with just the absolute value of the VFA.
Okay. I have about 2 more questions left here. One has regard to sediment that is floating within the reactor for one of our participants, and sort of what could be an indication of why that is occurring.
Well, we already talked about fog. I mean, I don't know if this is a dairy industry. I would be suspicious of fogs that could cause flotation. We've also seen flotation caused by polymers. We've seen that in the past. So that could be an effect. Also, of course, overloading itself. If you overload a system, and if it is a granular system and the sludge cannot really get detached from the granules because of an overload situation, then there may also be flotation of sludge. So this phenomenon can be caused by different effects. So you would have to look at that in more detail to be more conclusive.
Could also be the introduction of some solids to the system that were had a very low settling velocity that would float up also. So it could be a number of things. If we knew the industry, we might be able to help you answer it better.
Okay, and I'll be sure to pass that question along, and who asked that question, and we could follow up on that too. So we'll be in contact with you. One last question here before we close the webinar is that how important is it to stir or cycle the influent feed distribution line for UASB?
It is quite important because the distribution of flow over the bottom of the reactor is really decided by the design and the hydraulic conditions that you create at the bottom part of the reactor. So, I think this is something that we want to zoom into in our next webinar also when we talk about operational efficiency of reactors. But typically, the way we look at it is that if you create very constant conditions and controlled conditions feeding the reactor, that will also give you a very predictable and controlled flow patterns and distribution patterns. So and when we operate systems, we carefully take care of that. And we do that by recirculating effluent so that you're not dependent on influent flow for that.
I think, I'm not sure, maybe the person was asking about keeping the headers clean and doing what we call the header check or mixing the sludge. And it's important to do that on at least some sort of regular basis to ensure that those header lines are clear and all the nozzles are clear so that we can get the good distribution of water over the floor of the reactor that Rob was talking about.
Okay. Well, that's sort of, we're at our max on time. That is going to conclude our webinar. Please take note of when the next installment of this webinar series will be. We hope that you'll be able to join us. Jill and Rob, thank you so much for everything that you shared with us. And for any participant here who asked questions, thank you for submitting those questions. They're valuable to this whole community that we have on the call and on the webinar that could gain from hearing those questions and applying those techniques and tactics at their own facilities. So thank you for that. So please take a moment, fill out the survey after the webinar. We really appreciate your time in joining us here at Veolia. And if you have any questions or any additional needs, please do not hesitate to reach out to one of our technologists. So this concludes our webinar. Thank you and have a great day and a great weekend. Bye-bye.